is a photo that Kelly took in the Arctic of how far do animals sink in the snow, particularly with regard to whether or not they are going under canopies. And if you can do next slide. If you can't hear me, just Kelly has to. I'm gone. I can't.
Sorry, I was struggling with Zoom there. Can you guys see my screen?
Yes, we can.
On a background slide?
Yep.
Okay, was this Kelly talking about this one?
It was Jessica, but I think we might have lost her.
Oh, okay.
Jessica, are you still on? I guess not. I'll jump in here. So we're interested in taking this diverse data set and doing something you can't really do with it, which is look at snow strength. And we did have some proxies for strength, but we were interested in this animal mobility problem. And there's lots of work out there looking at effects of density on mobility, but that's just part of the picture. And we wanted to see if we could integrate some of our other data sources into this problem. There's also some discussion about how collared animals tend to run for the woods. And we were interested if that was because they know that the snow is shallower and less dense there and they can move around, or if they're just hiding behind trees. So there's a little bit of a sociological ungulate question there too that we also can't answer. But we set ourselves up for failure right at the beginning and worked hard to try and reverse that. So next slide, Sam. Snow density being the primary factor that wildlife people tend to use for strength. We did have good density measurements on the mesa. We recognized the part, we pulled out a chunk of the data set that you'll be able to see spatially in a minute, but it was a fairly limited area and it had basically a binary snowpack. And that's open areas that were heavily snowmobiled and windblown, and forested areas that had little snowmobile activity and lots of cover and of course interception, so a shallower snowpack. So we tended to have forested weak snow and deeper, denser, stronger meadow snow, if you will. And you can see a couple of snowmobile tracks in this thin section, this backlit thin section from a pit wall from one of the campaigns. Let's see what else. I think I covered that. Go ahead, Sam. And just a quick summary of this, to take this into the hardness realm instead of the density realm, we did have some hardness type data. The density, the problem is it correlates poorly with strength through the range that we're kind of interested in, which is very typical in the Rocky Mountain Cordillera on a seasonal basis, and also is typical of a lot of the predator prey habitats that we're interested in. So from a roughly 220 kilograms per meter cube to 300 kilograms per meter cube, it really depends on grain type, which is a proxy for number of bonds or bond strength per unit volume in a snowpack. And so we tried to get at this some different ways with the data. And these are just two pictures of examples. These are roughly the same scale, both magnified. One is equilibrium or rounds on the left, and the other is faceted or kinetic snow on the right. And the grains themselves are very strong in terms of facets, big ice objects, but they tend to have few bonds per unit volume, and the bonds themselves may be very strong compared to individual bond in the rounds, but there's just not very many of them. So the SMP does in fact provide some data for that, as well as the hand hardness measurements that we did in the field. They're both good proxies for strength, although not directly transferable into a strength value. that anybody's figured out that I know of. So I think you can go on, Sam. And that's where someone else takes over.
I guess I can cover the map since I made it. So we selected some sites based on essentially visually how forested the areas looked based on national land cover categories. So you can see the primarily forested sites are in green, and then the sparse sites, which we tried to pick ones that were on borders of forests, were yellow, and then open sites, which are colored in black. And then the scale here basically goes from green to white, where green is more dense forest. And that's what I have to say about that map. Was Jessica going to do this question? Is she back yet? For this slide?
I could do the question.
Okay.
Or you found a picture of me for that slide too.
Yeah.
So so basically with those classifications of dense, sparse, and open, we wanted to know, how does forest cover affect snow density, SMP measurements, and hand hardness? I don't remember if we ever got to hand hardness, but we started by wondering like what actually is forest cover, and is forest cover in the actual pits that we dug the same as what you might get from Chris Heimstra's classification in the 3 categories, or what you might get from a LIDAR national land cover data set. How does the total pit depth and density vary by forest cover? How does modeled pit depth and density vary by forest cover using snow model? And how does SMP vary by forest cover?
Sorry, can everyone hear me? Can I just get a thumbs up here? Okay, great. Yeah, sorry, I'm kind of working from an appointment here, but I can quickly go over our first step, going through the methodology here. So we were able to write a program essentially that organized these photos into, or from the SnowEx data set into an easier view and organized format. From here, we used the data frame to label these photos by north, east, south, and west, and generate 360-degree views of specific pit sites that we had designated. I then continued to use the criteria from the SnowEx Hackweek site that in an attempt to make a visual observation of canopy cover and designate between either a dense canopy, sparse canopy, or open canopy. I then compared the canopy density from these 360-degree views to canopy cover that we had initially chosen from our sites from the land cover data. This comparison of the remotely sensed data, it's important to use this kind of ground truthing because it helps to establish error of the remotely sensed classification, and helps essentially to validate our analysis and our conclusions. Next slide.
Yep, now it's my turn. So in order to kind of compare those photographs to a bit of validation data, we looked at these vegetation layer, canopy height metric. And so we first started playing with the data that was provided in the ISO tutorial, but after about a day's work on that, I realized that those areas were outside of where we dug all these snow pits and took all these photos. So we kind of had to start over from square one on like day 3. And thanks to Anton, we pulled some open topography LiDAR data that was collected a few years back, and we're able to difference the min and max from a couple different acquisitions there to create a new canopy height layer that covered Grand Mesa. And there are a few steps of data processing, like filling voids in those images to get them to work right. And next slide. And so from the canopy height data, we use this metric, which is known by a few different names here. It's called the Canopy Fuel Estimator, which is U.S. Forest Service methodology. And essentially kind of moving through all of the points in a window, it shows a radius of 5 meters. You calculate the ratio of canopy above 2 meters versus the total number of pixels in the image. And that's what's presented there. And this calculation took quite a bit of compute hours, about 2.5 hours to move through this image, which has got 31.5 million pixels. So I had to drop a rock on my keyboard in order to keep the Jupyter notebook running. Next slide. That was a Hack Week tip for everybody out there. So then we use some of those tools that we learned from the ASO tutorial in order to upscale these rasters. So we upsample them from 0.5 meter canopy cover to 30 meters. And then just by kind of thresholding that CFE variable, we were able to classify this into either open, sparse, or dense forested areas. And in this way, we now have got a metric to compare, another metric to compare the canopy density to our observations. Next slide. I think that's all I've got to say.
Yeah, well, it looks like the text went away, but yeah, again, oh, there it is. Thanks, Sam. I think there's 3 bullet points. So, but yeah, so even though all of the points that we made about how looking at density can be problematic, we decided to do it anyways, and look at it using different canopy classification methods in both, open forested, sparse areas, using the pit data. So I think we chose 15 pits, and those are the same that Anton and Tate were talking about earlier. But as we can see on this left image, this is just all of the pit data. So not integrating any of the other canopy cover methods. And we can see that the density throughout the profile might not necessarily be the best metric for us to use. So we also investigated averages in the top 10 and top 50 centimeters of the pits. So you can go on, Sam.
About 2 minutes left.
Yeah. Okay, sweet. And these are our results. As we can see, the canopy classification methods did a pretty good job. There's some discrepancies. You can see the photo canopy classification method that Meehan did, the field canopy method, which is just the field from the field notes, and the Tate CFE method. And we see a general trend here of denser snow and deeper snow and more open areas, which supports that our knowledge about wind-blown effects in open areas and snowmobile impacts. So this also supports the fact that it'd be really awesome to integrate some of that hand hardness and grain property metrics into this data.
Cool. So to get a broader picture of how canopy cover influences snow density, we wanted to model snow density between the pit measurements and across the entire study area. For this, we used a snow model to model average snow density over Grand Mesa. Snow model is a physically based, temporally and spatially distributed snow evolution model that was developed by Glenn Liston and Kelly Elder. Thanks, Kelly. For this model, we used a DEM from the National Elevation Data Set, land cover data from the NLCD database, and we used meteorological data from the SnowEx 20 Cosmos station. And then as a final step in the modeling process, we assimilated snow pit density measurements to produce a correction field. This helped to correct snow density to those values observed in the field and help to reduce time and calibration and validation of the model, given the short time frame. Next slide, please. So here you can see the results of the snow density model. Darker blues represent lower density and the lighter values represent higher density. We can see that the highest densities are located around or within the forests and off the edge of the mesa, whereas the lower values are mostly relegated to the open areas. Next slide, please. So from these modeled rasters, we produced a density plot of this, so density in terms of statistical density of the snow density separated by the different LiDAR measured forest classes to see how canopy cover affects snow densities on a broader scale. What we found is that open areas typically experience the lowest snow densities and sparse areas at the highest, where dense forests, where dense forests have snow densities kind of somewhere around in the middle. So there seems to be like an optimum amount of canopy cover that's associated with the highest snow densities. Too much canopy cover or too little seems to be associated with generally lower snow densities. Our thinking here is that snow model isn't really great at capturing the full picture of how canopy cover affects snow density. It's likely that these snow density differences are primarily driven by snow depths. So what snow model is probably capturing is the wind blocking effect of the canopy cover and how wind distribution of snow affects the subsequent snow compaction. So it blows around and then you get these more snow in certain areas that compacts the snow and produces higher densities. And then the sparser edge regions on forests are probably capturing most of this snow moved from the open areas by wind. And that's probably why we're seeing the highest densities in these sparser regions. But still, we didn't really have time to fully explore these trends. And it's definitely an interesting question that should be investigated further in the future.
So beyond looking at density, as Kelly mentioned, that may or may not, or it doesn't tell the full picture of strength. So the snow micropen, the SMP, is kind of like a elk hoof or a wolf paw going into the snow. So we thought we'd get that data at some sites in the trees and some sites in the open. So first we had to pulled the SMP profile nearest the snow pit, which thanks Mike Duran for that tutorial on how to do that. And Micah also helped out a lot getting this data. So we pulled the raw data there, and it's a little tricky because you don't know where the surface of the snow is and where the ground is. So I actually, because there's it's subsampled the data on the database, I manually classified the snow surface and the ground. So the snow surface is where the snow micropen's been going through air for a while and then hits the snow. And the ground is at the bottom where you get a huge force value as you go down. So classified those for some SMP profiles near our snow pits, plotted just the section through the snow. And then we don't know what the best metric is for like animal hoof penetration. So we thought we'd just get a few. We went for median force across the whole depth, mean force across the whole depth, which also will like be a higher value for if you have a thicker crust. So we're kind of guessing that's going to be a better estimate for penetration. And then also just the pure sum of measurements on the top 10 centimeters of the snowpack and the pure sum of measurements for the top 50 centimeters of the snowpack.
We're a couple minutes over, guys.
Oh, sorry.
Okay, and I can go over this real quick. Essentially, this is kind of what the results I've found from kind of the photo classification and the site classification. Essentially, there was a 56% difference between what was observed and what was classified based on the remotely sensed data. And I kind of tried to put this into a simple visualization here. So essentially, like, if we are using that site classification method, it really isn't as accurate, or it's not, I don't know, it's not as good of a method for making conclusions. So yeah, next slide.
Okay, and looking at the snow micropen results, all 4 of those metrics show a harder snow in the open area is the takeaway there. Kelly, you want to wrap it up? Or whoever made the slide?
I think Kelly made the slide that wrap it
Sure,
up that we didn't have any good foot sinking data except for the few photos. But we was a great group of people and we had a great time, and I know who to ask questions when I can't get my things to work. Kelly.
Yeah, I guess the one other thing I would say is that this data set is, you should really think about it when you use it because of the snowmobile influence there. And this is going to be a common problem in lots of the Western US with outdoor recreation and the increase in that. Lots of our big open areas that are on public lands are heavily used, and pretty much every weekend this place gets obliterated by snowmobiles. And physics-based models should do fine with that because it's a physical thing. Some of the assumptions that we make about natural snowpacks will violate things that you do with these data. And that's a good example with snow model. It doesn't handle compaction by snowmobiles, but it does handle compaction by wind transport, which is part of the story at Grand Mesa. So just a word of caution moving forward with this data set. That could bite you in some places and probably not in others. So it was super fun and a great group. Thanks.